So the last part of the homework assignment for Module 2 involves the application of the switch case statement to the simulation of a half-wave diode rectifier. Now, this simple circuit is something that all electrical engineers are exposed to in their sophomore circuits class. We're not going to go through the theoretical details here since our focus is on the use of MATLAB, but very briefly I'll remind us of how this works. So we've got a source here, sinusoidal voltage source that's then in series with a diode, and then finally a parallel combination of a capacitor and a resistor. What happens is as the source voltage increases and is positive, then the diode is switched on, current flows. When the diode is on, then the voltage, initially the voltage building up across the voltage source is mirrored on the load resistor, and simultaneously current is flowing into the capacitor and charge is building up on the capacitor. Now later on the source voltage starts to drop. When it starts to drop, then the source voltage drops below the voltage that has built up across the capacitor. Then the capacitor discharges. Since the diode, of course, only allows current to flow in one direction, then the capacitor is discharging through the resistor, and what we'll see is that the voltage across the resistor gradually drops off as the capacitor discharges. Eventually the sinusoidal voltage source builds up again and turns on the diode, and again charge builds up across the capacitor and voltage across the resistor. So if we actually take a look at what happens when the simulation has been put in place, then what we see for a 10 microfarad capacitor in this particular case, we'll look at the details shortly in terms of the other parameters, but as the source voltage builds up, then similarly the blue is the voltage across the resistor. So as the source voltage builds up, then the voltage across the resistor builds up. As the source voltage decays, then the capacitor discharges through the resistor, and so the resistance, the voltage across the resistor decays much more gradually, and then eventually the source voltage builds up again, and the load voltage, the resistor voltage, mirrors that, and then until the source voltage turns around, capacitor discharges, and it keeps on going. Now, if we're trying to, say, get the peak values here, you can obviously control the rate of decay through the value of the resistor and the capacitor. We know that the product of R times C gives us the time constant, and so you can control the rate of decay through your choice of the resistor and the capacitor. If we hold the resistor constant, which is sometimes the case if you have a particular load resistance, then you can change the parallel capacitance in order to change that time constant. If we increase the capacitor from 10 microfarads to 50 microfarads, then we get this result. So we lengthened the time constant by a factor of 5, and so we see that it takes the voltage across the resistor is decaying much more slowly, and so you get a smoother result if you're trying to, say, capture the peak values here. All right, so let's take a look inside the MATLAB template. You will be completing this for your homework, but again we start off by clearing out the memory, closing all the figure windows, We'll specify the amplitude of the source voltage to just be unity, nothing particularly special about that, just convenient. We'll pick the source frequency to be 60 hertz, so that's like our wall outlet, our electricity at home. We'll specify the value of the capacitor, and in this particular case I'm specifying it in microfarads. The UF is to designate microfarads, which I then have to turn around and then convert over to farads by multiplying by 10 to the minus 6. Now, the reason I want to capture the value in microfarads is because I want to use that on the plot. If you look back at the plot, you would see that the title actually had the value of the capacitor in microfarads spelled out. So I wanted to separately keep a variable that had the value in terms of microfarads, but then in terms of the actual equations, we need it in terms of farads, so we have that. We'll specify a 2K ohm resistor, just a convenient value to use. And then we will specify the time vector. Now I'm wanting you to fill that in, but I want it to start at 0. I want it to go up to 70 milliseconds, and I want it to be in increments of 0.1 milliseconds. And you should put in an expression there that will provide that time vector. Now the source voltage is the amplitude. We're going to do a sinusoid, and 2 pi times the source frequency, and then the time vector that we just specified up here. So this will give us a vector of the voltage of the source over the time interval. I'm giving you what the switch variable is. We're calling it diode, and then we'll start it off by initializing it to be on. Now this is a character string. Don't get this confused and think that this is a Boolean variable or something like that. That's not the case. It's just, the diode is either on or it's off. So we have a character string here to start it off. We'll say it's on to begin with. And that's because the voltage source is going to be positive to begin with, and so we know that the diode's going to be on to begin with. Then we're going to need to loop over that time vector. Again, you're going to need to insert the proper MATLAB code to loop over that time vector. You'll see that I'm specifying the time variable as k. You don't want it to be t because, of course, t is the vector itself, and you need to loop over every index. So k is essentially the index that goes through every element of the time vector. Then we're going to need to set up the switch structure. So in this line, you're going to need to insert the proper switch code. The single percent signs are comments. The multiple percent signs indicate lines that you need to replace with MATLAB code. So then you need to insert the code for the case where the diode is on. Then we have all the mathematics that is associated with the circuit analysis. Again, this is not a circuit analysis class, so we're not going to go through that detail. But we're specifying the resistor voltage, the current through the resistor, the current into the capacitor, and the current through the diode, which of course is the sum of the resistor and capacitor currents by Kirchhoff's current law. And then we're keeping track, because once the diode current goes below 0, then the diode will switch off, and we need to change the switch expression then to off, and we're going to need to keep track of that time at which the diode switched off, because that will impact the expression for the values during the time that the diode is off. So you need to insert the code here for the case. Say, okay, the case is the diode's off, and in that case then the voltage across the resistor is given by this expression, and the key here is that that decaying exponential is given by the elapsed time after the diode turned off. So that's why we needed to keep track of the time at which the diode turned off, because it's the elapsed time after the diode turned off that governs this this time constant, this e to the minus t over over RC. Then we keep track. We look to see if the source voltage has increased up to the point where it is larger than the resistor voltage, and at that point then we know that the diode has turned back on again, and then we can go back to the top of the time loop and do it all over again. And we've got some plotting statements at the bottom, and you recall that we had kept track of what the value of the capacitor was in terms of microfarads, and this line here allows us to specify the title, and it's a series of strings. This is string concatenation, and so I've got a string, it's half-wave diode rectifier for C equals, then num to string, so I'm taking the number, which was that value of the capacitor in terms of microfarads, turn that from a number into a string, concatenate that with the previous string, and then also, and this backslash mu gives you the Greek letter mu for micro, and then attach that to capital F for farads, and so you end up with half-wave diode rectifier for C equal to, in this case would be 10 microfarads, and it'll show up in the plot accordingly. All right, so for your assignment, you'll insert all these lines of code in order to get the thing to run. Again, the focus here is on the switch case statement. You'll also need some need a for loop in there, and you should be good to go.